Hi everybody. Today this is a lecture on section 9.2. Section 9.2 is on the fundamental theorem of finite abelian groups. Fundamental theorem of finite abelian groups says the following. If G is a finite abelian group, then G is isomorphic to a direct product of cyclic groups. Okay. So this is going to allow us to characterize up to isomorphism all finite abelian groups. In conjunction with this, remember the following two facts. Remember the following two facts. One, cyclic group Zm cross cyclic group Zn has order, right? Order of these two, Mn. Two, cyclic group Zm cross cyclic group Zn is isomorphic to Zmn if and only if, and we proved this last semester, GCD of M and N is 1. Okay? So in conjunction with these facts will allow you to characterize all those finite abelian groups. Okay? So, for example, let's say the order of G is 6. Assume G is abelian. And the order of G is 6. All right. Well, what cyclic groups can we get whose orders multiply to 6? Of course, there's Z6 itself is isomorphic to Z6. Which is also isomorphic to Z2 cross Z3, right? They're the same thing. So that's it. Okay. So G is isomorphic to Z6 or Z2 cross Z3, but they're the same group. What about if the order of G is 8? Well, so G is isomorphic to cyclic groups whose products, whose orders multiply to 8. Right? Well, there's Z8, of course. Right? There's also, what else? Z4 cross Z2. And there's also Z2 cross Z2 cross Z2. Right? This has got order 8. It's got an element of order 8, cyclic of order 8. This guy is not cyclic, but it has an element, right? 1, 0 has order 4. And this guy, every element has order 2. Right? So every non-identity element has order 2. So these are three different abelian groups of order 8. Z2 cross Z2 cross Z2 is order 8, but different than Z4 cross Z2. It's got order 8, which is different than Z8, which is also different than that. Right? So three distinct groups. But with order 6, because Z2 times Z3 is isomorphic to Z6, you only get one there like that. But here, none of these guys are isomorphic, and that's it. Okay? That's the only ones. There are no other finite abelian groups of order 8 because we've exhausted all the possibilities for direct products of cyclic groups. Right? So that's order 8. Order 10 is, well, there's the cyclic group of order 10, but then 10 is 2 times 5, which are primes. So that's the same as, right, Z5 cross Z2, or Z2 cross Z5. Oh yeah, also, by the way, right, I mean, Z2 cross Z4 is certainly isomorphic to Z4 cross Z2. So, you don't have to include that sort of thing. Right, Z4 and Z4 cross Z2 is the same as Z2 cross Z4. It's not the same, but they're isomorphic. So if you're order 10, then this is all you've got. What's next? Order 12. Right, so order 12, well, what do you have? We could be cyclic, Z12, right, which is the same as Z4 cross Z3, yes. But that's not the only thing, because for order 4, you don't just have Z4, you've also got, right, Z2 cross Z2. Right, so you also have Z2 cross Z2 cross Z3, which of course is the same as the Z2 cross Z3 is the same as Z6. Is the same as Z6 cross Z2. And that's it. Alright, so Z12, same as Z4 cross Z3, and Z6 cross Z2 is the same as Z2 cross Z2 cross Z3, because the Z2 cross Z3 is Z6. Okay, 14, Z14, same thing, because it's 2 times 7. There's order 14 is just Z14, because 14 is 2 times 7. Order G equal to 16, this is a little more interesting. Right, that's 2 to the 4th, so you can have Z16. You can have Z8 cross Z2, right, this is cyclic, this one is not. But not just Z8 cross Z2, we could also have Z4 cross Z4. This guy has an element of order 8. Right, this guy does not have an element of order 8. Right, so these two are not isomorphic. Forgot the word or. Or. What else are we missing? Z4, Z8, Z2. There's also Z4 cross Z2 cross Z2. Right? This guy is different than that one. Right? If you counted up orders of elements, you'd see that they were different. This one has more elements of order 2 than does this one. This guy accounts for 4 elements of order 2, and this one has 2. So this guy's got 8 elements of order 2. Well, 8 elements of order 2 or less. This guy has only got 4 elements of order 2 or less. Right? Because the only elements of order 2 are 0, 0, 0, 2, 2, 0, and 2, 2. Right? So, and then there's one more. What's that last one? Z2 cross Z2 cross Z2 cross Z2. Right. So 16, you got quite a few. Got 5 there. 1, 2, 3, 4, 5. With 8, you've got 3. All right. So the fundamental theorem of finite abelian groups. Every finite abelian group is isomorphic to a direct product of cyclic groups, and then using the following 2 facts as the order of Zm cross Zn is m times n, and Zm cross Zn is isomorphic to Zmn if and only if GCD of m and n is 1. M and n are relatively prime. So with those facts, you're able to list out via exhaustion all of the possibilities for any finite order. It takes you a little while as numbers get larger, but it can be done. So let's talk about a proof of this. Okay. Okay, the proof will take several parts. One moment. Okay. So first of all is a lemma. And the lemma is as follows. No. So say that the order of G is P1 to the E1, P2 to the E2, times Pm to the Em, where P1, P2, all the way up to Pm are distinct primes. Okay, so we've written it like that. Now let the order of G like that. Let A sub Pi be the set of all G in G such that the order of G is a divisor of P to the EI. Okay, so the order of G, well, I could say the order of G is equal to P to the, let's say, Fi, right, which is a divisor of P to the Pi to the Fi, which is a divisor of, I'll just leave it like that. So any element whose order is a power of P to the I. Okay, and of course that's going to be a divisor of this group, so this exponent Fi must be less than or equal to Ei. Okay, so note that 1 is an element, so I'm writing the group multiplicatively, okay? In the book, when they do this proof, they write they write most of it additively, but I think it makes a little more. I think it's a little easier with multiplicative notation. I don't know. I mean, it could be just me being prejudiced or something, but there it is. But notice that 1 is an element of API, so API is not empty. Okay, it is. It's actually going to be a subgroup. Okay, you can show that API is a subgroup of G, but we'll leave this part out. That's something that we've done many times, showing things are subgroups and things within abelian groups are subgroups. So it's kind of old hat at this point. Okay, what else do you notice about the two different API and APJ? If I is not equal to J, then API intersect APJ. Well, it's the set of all elements whose order is, right, so I mean if like PI was 3, 3 to the K, the set of all elements whose order is a power of 3, and the set of all elements whose order is a power of 5, right? But there's no common divisor between powers of 3 and powers of 5 except for 1. Right? And the only thing of order 1 is just the identity. Right? So if I is not equal to j, then these two guys have empty intersection. Now what am I getting at? Okay, remember from section 9.1, the main result. And I'm going to write it for more than two subgroups. The main result for the theorem of section 9.1 is as follows. So we'll say subgroups N1, N2, all the way up to Nk, I guess, are normal subgroups of G. So we're talking about abelian groups. Every subgroup is normal. If N1 to Nk are subgroups of G such that 1 Ni intersect Nj is just 1 for every I not equal to j, and 2, G is equal to the set product, like that, then G is isomorphic to N1 cross N2 cross Nk. Now, this was stated for two normal subgroups in section 9.1, but, it generalizes to 3 or more normal subgroups very readily. Okay, so this is what we're getting at here. Okay, remember the main result from section 9.1. If you have a bunch of normal subgroups of G that pairwise intersect, not this, not totally intersect, that totally intersect in the identity. No, each pair intersects in the identity. You can have like 3 or more sets intersecting in the identity. One, 3. All right, the intersection of these two is 2, and the intersection of these two is 3, but the intersection of all 3 is empty. Right? So if you got a bunch of normal subgroups, such that every pair intersects in the identity, and G is the set product of all those subsets of G, then G is isomorphic to the direct sum of those subgroups. So that's what we're going for here. We want to show that G is isomorphic to the direct sum of the APIs. Right? So first of all, we've shown that the APIs for API and APJ, that they intersect in the identity, because there can be no common element whose order is both a divisor, power of p and a power of j, except for one. Power of p to the I and p. A power of p sub I and a power of p sub j simultaneously, because they're different primes. Okay, so now if we show that, G is equal to AP1, AP2, all the way up to APM, then we will have that G is isomorphic to AP1 cross AP2 APM. Okay? In order to prove this, let's do a little bit of a lemma. Suppose A is an element of G, and the order of A is equal to, let's see, what letter should I use? Let's say G. And the order of G is equal to A times B when GCD, or with GCD AB equal to 1. Okay, suppose you have that G as order AB, where GCD of A and B is equal to 1. And A and B are not 1 themselves. Okay? Then G will be equal to HK, where the order of H is A and the order of k is equal to, b. Okay, so we're going to prove this lemma. Right, if the order of g is a times b with GCD of a and b equal to 1, then g is going to be equal to hk, where the order of h is a and the order of k is b. So we can sort of split it up like that. Proof of the lemma. Because GCD of a and b is 1, there is S and T and Z such that 1 is equal to AS plus BT. This also implies that remember that the GCD of two numbers can always be written as a linear of two integers can always be written as a linear combination of those two integers, right? And that the GCD is the smallest positive such linear combination. And of course, 1 is the smallest positive number there is. Positive integer there is, sorry. So not just GCD of A and B is 1, but the GCD of S and T is 1, of S and B is 1, and T and A is 1. So GCD AB is equal to GCD AT is equal to GCD SB. GCD ST equals 1. All right, so all four of those numbers are pairwise relatively prime. So now, G is equal to G to the 1 is equal to G to the AS plus BT is equal to GAS GBT. Now, where G, period. So notice GAS to the B is equal to G to the ABS is equal to G to the AB to the S is equal to 1. Right? The order of G was A times B. That was our assumption. The order of G is A times B, so that's 1. Right, so the order of G to the AS is, sorry, so B divides the order of, divides B. However, there can't be a smaller integer than B, so that G to the AS to the M is equal to 1, right? Because the GCD of A and B is equal to the GCD of A and S is equal to 1. There cannot be any smaller exponent than B, I guess. So that G to the AS to the M is equal to 1. Well, why is that? Because the order of G is A times B, right? So any exponent that you raise G to that's going to be equal to 1 has to have all the prime factors of A and B included. All the prime factors of A and B have to be included for a power of G to be equal to 1. Right? But none of the prime factors of B are in A because they're relatively prime. None of the prime factors of B are in S because they're relatively prime. And M is less than B, so it doesn't have all the prime factors of B. Could have some, but not all. Okay? So the order of G to the AS equals B. And similarly, the order of G to the BT is A. Right? And, G is equal to the product of those two guys, as required. Okay? So now, that's the end of the proof of the lemma. Okay, end of the lemma proof. So now, let's go back to G. Right? We have these subgroups of G, API. It's the set of all elements of G whose order is a power of pi, or pi is a prime. And we know that the intersection of any two API and APJ is 1, because you can't have an order, a power of 3 and an order power of 5. That's the same except for 1, right, which is the order of the identity element. So we want to show now that every element in G is a product of, some things in the APIs. Okay, so now, if G is in G, then the order of little g divides the order of G. So the order of little g is equal to P1 to the F1, P2 to the F2, Pm to the Fm, right, where each Fi is less than or equal to Ei, where P1 to the E1, P2 to the E2, Pm to the Em was the order of G. So if you're going to divide the order of G, then you're just lowering those exponents some, if anything. Okay? But this is exactly what the lemma is doing here. Right? The order of G is A times B, with GCD A and B equal to 1. So here you've got that. The order of G is, well, it's this times that, and they're relatively prime. Right, so G is equal to G1 times G2, or G1 times H1, where, so we repeatedly apply the lemma. So now, since the PIs are distinct primes, we repeatedly apply the previous lemma. Right, we repeatedly apply the previous lemma to get the following. To get that G is equal to G1 H1, where the order of G1 is P1 to the F1, and the order of H1 is equal to P2 to the F2, Pm to the Fm, right? And then G is going to be equal to G1 G2 H2. So where H1 is G2 H2, where the order of G1 is P1 to the F1, the order of G2 is P2 to the F2, and the order of H2 is P3 to the F3 all the way up to Pm to the Fm. So you keep peeling off one prime at a time. Right? So the order of H1 was this, so we peel off the P2 to the F2, and then etc., etc. G is going to be equal to G1, G2, all the way up to Gm, where the order of Gi is Pi to the Fi. Okay. So that's what we wanted, right? That G is a P1, a P2, a Pm. So G is isomorphic to a P1, a P2, a Pm. All right. What is the order of API? What is the order of API? Remember Cauchy's theorem. We didn't finish the proof of Cauchy's theorem for non-abelian groups, but we did do the proof of Cauchy's theorem for abelian groups. So we're not quite done with Cauchy's theorem yet. Where is it? Cauchy's theorem. Right there on the website. If G is a finite group, any finite group, G is any finite group, and P is a prime, if P divides the order of G, then there is an element in G that has order P. There is an element in G that has order P. So that's for any group, abelian or non-abelian. We have not finished the proof, but we did do the proof for abelian groups so far. So that's proof of Cauchy's theorem for abelian groups. Proof of Cauchy's theorem for non-abelian groups. Well, I was hoping to get time to do it, but we haven't quite gotten the time yet. But we'll get to it. So, we've got Cauchy's theorem for abelian groups at any rate. All right. So, by Cauchy's theorem, well, by definition, each Gi in API has order a power of P to the I. So the order of API is also a power of P to the I by Cauchy's theorem. Because if some other prime Pj divided the order of Pi, then there'd have to be some element of order Pj. But there isn't by definition. There isn't by definition. So the order of API is a power of Pi. And now because G is equal to it's isomorphic to AP1, APM. We must have that. The order of G is equal to the order of AP1 cross, that P1 to the E1, P PM to the EM, which is equal to the order of G, is equal to the order of these guys, A P1 times order A P2 A PM. Right, but this guy, his order is the power of P1, so it's got to be P1 to the E1. This guy, his order is a power of P2, so it's got to be P2 to the E2. So the order of API is equal to Pi to the EI. All right. So G is isomorphic to a direct sum of groups of prime power order. Now all we have to do is show that every group of prime power order is isomorphic to a direct product of cyclic groups. So let's write that down. So every abelian group is a direct sum, is isomorphic to So now all we have to do is prove that a group of prime power order is a direct sum of cyclic groups. So all that is left is to prove that any finite abelian group G, where order of G is p to the n, is isomorphic to a direct sum of cyclic groups. Okay? Right, we have that any finite abelian group is isomorphic to a direct sum of groups of prime power order, right there. G is isomorphic to these APIs, and each API has prime power order. It's isomorphic to a direct sum of the APIs, where the APIs have prime power order. So now if each one of the APIs is a direct sum of cyclic groups, then the whole thing is a direct sum of cyclic groups. So we've reduced the problem for all finite groups, finite abelian groups, to all finite abelian groups of prime power order. Okay? So that's the final part of the proof. So it's long and involved. This is definitely like the most tricky theorem that we've proved in the course thus far. Now here it is. The proof in the book for this part is really just impenetrable, I think. I mean, I was reading it and it's confusing, to say the least. I know why he did it that way. He did it that way because, you know, it's lemma 9.6 in the book on page 291. And then page 292 is, the whole proof is on page 292. And it's pretty opaque. But it's a slightly stronger statement. But I don't think you need the slightly stronger statement. I mean, just to prove the finite, to prove something a little more than the fundamental theorem of finite abelian groups, you would need that. But that little more is not that useful here, I don't think. So I think a more accessible proof of the fact that this guy is, not this guy, this guy is a direct sum of cyclic groups is preferable. Okay? So the proof is by induction on N. On N. Okay, so the base case this is 39 minutes already. Let's go a little bit more. Oh no, I guess we have to stop now. We'll do that proof next time. Okay. So we'll have an assignment posted for section 9.1 and 9.2, and we'll do the rest of this next time. Okay, so